Hello and welcome, Florian.
Thanks. Hi.
So you're here today as demoing the Toit platform.
Correct. Yes.
Yeah.
It's a big project at Toit. Yes.
Yeah. And perhaps you can tell us a little bit on who you are and the Toit company, or maybe you already have a slide for that, or
I have a partial slide for that. So I think the easiest is probably just to do it in the slides then. Yes.
Yeah. I can just bring a little, very short backstory on why you're here. I stumbled on your project, I think it was maybe 3-4 months ago, and I was so amazed that you were able to run containers on the ESP32. This was totally new, and I guess it still is totally new. I'm not sure if anyone else is doing this, but for me, it's like when we're talking about embedded devices and what has happened like the last years is that well, you were at the beginning, you had to be good at programming in low-level languages like C++ or even assembler maybe longer time ago. And then something happened that MicroPython came along, and now there are other languages creeping down. You can program in JavaScript, Go, also on embedded devices. But now something else is starting to happening, which I think is so interesting, is that, we've been running these Docker containers for so much time, like everything is Dockerized. We have this containerized application. And now that is also creeping down onto the embedded devices.
Yeah, I mean, I would say that the term container is a little bit abusing the term in some sense, and I will mention that in the presentations. And I mean, we do containerize applications, but they must be written in our language. So it's not like we can just start a new Linux, Alpine Linux on the ESP32. That's not going to happen. But on the other hand, yes, we do containerize applications. We separate them. We make sure that they can't interfere with each other and have their own resources and similar things. So from that point of view, we do actually have containers, and you can update one without changing the other, keep them running. So there are definitely some features of containers that we do have, and that's why we also mentioned them on our homepage. We do containerize applications. That's true.
And that's really like just looking at like the embedded sphere, the IoT sphere, is that like whatever happens like in the cloud is sort of creeping down also to the smaller devices. So
this yes, I will mention it again in the presentation, but that is fundamentally what we try to do: make the development of these small microcontrollers a little bit more like real developments, not just this old 20-year-old style. I have a microcontroller and write something, flash something on it. So yeah, that's basically a short summary of my presentation. Yes.
Yeah.
That's what we're going to try to do, or what we're trying to do.
Okay, but you have a screen share. So
yes, I will share my screen. So I think that should be on now.
Yes.
And I will go to full screen, and from then on I will not see you anymore. So just say something if something is wrong. Should be set up now.
Yep, it's fine.
Good, then I will just start. So I'm going to present Toit, and as we just discussed, it's a little bit more than just containers, and we will see why and how it works. So before introducing a little bit more myself and our team, I want to just start with where do we come from? Why is this even happening? What is this about? And fundamentally, everything starts with the ESP32. And the reason is that, we discovered this chip a few years ago, and it's just an impressive microcontroller. It has 520K of RAM, which is not completely true. They're not all usable, but they advertise it as such. This module at least has 4 MB of flash. It's a dual core 240 megahertz, has Wi-Fi, Bluetooth, analog to digital converter, digital to analog converter, pulse counters, infrared modules, Hall sensors, all kinds of stuff, and the whole thing for less than $2. And $2 is pretty much what you pay when you try to buy them yourself. If you buy them in bulk, you probably get them for maybe $1. So it's really massive. They're really powerful, and yet it's frustrating how these are programmed. They are basically treated like microcontrollers from 20 years ago. Pretty much 20 years ago, yes, I actually worked on Atmels and 8-bit microcontrollers, and the development process most of the time is similar. You write your program, you compile it into one big chunk, and then you flash it on the device, and that's it. Then you run it. There is no real notion of applications, no separation of memory, no resource control. One wrong program or one wrong line can just bring down the whole system, and yeah, that's it. And while it's not completely true anymore that there's no high-level languages, it's still mostly true that most of the time people try to stay with C, C++, or low-level languages. MicroPython and CircuitPython are trying to basically run on these, but I would say they're not production ready. Maybe people will disagree, but they do have their issues. They're a little bit slower often, and they're not necessarily deterministic. They're sometimes crashing when other times they don't. It's not always the best experience.
Yeah.
Here's now basically what I just said, how the traditional stack and why this is a problem, or why this happens. So you have this ESP32 chip, and it has the 3 RTOS on top, and then basically you have this big chunk that you write, and it's you have all the system functionality, you have no protection, you're just running as if you were the operating system, or together with the operating system, and that just has issues. And this is now where we come in. So our team basically decided to fix this. We met at Google around 12 years ago, and then worked on V8 and the JavaScript engine of Chrome, and then Dart, the language that is behind Flutter. If you haven't tried Dart and want to write phone applications, I definitely recommend Flutter. It's great. And just as a side note, Casper's, so one of the co-founders, master's thesis was titled Revolutionizing Embedded Software. So even, 15, 20 years ago, he already thought of trying to make this better, and then just ended up at Google instead of doing this a little bit earlier. And I think he just got frustrated and thought that even then he could have done it, and it was still not done. So let's do it now. And we agreed, and we joined him in doing this. So that was 3 years ago, I think, maybe. And few of us Googlers, we then started a new startup, Toit, and did this project.
Yeah, and when you say Toit now, that you're based in Denmark.
Yes.
Yeah.
We are all based in Denmark. We joined from Google, some from Uber. We grew a little bit, shrunk a little bit recently, but we're still working actively. And we're all based in Aarhus, and that's where actually V8 was started. Now it's in Munich. And yeah, it's great. It's really nice to work with these people. And yeah, the goal was basically make the development of microcontrollers as easy as normal development. I'm mentioning here cell phone applications, but it's also true for normal applications. You want to write applications, install them separately, update them independently, make sure that one application doesn't interfere with another, use a high-level language, and obviously it should be fast. And this is also where now the containers come into play. If you want to satisfy these first 3 bullet points, you have to basically containerize them. You cannot protect applications from each other if you don't put them into containers. So from that point of view, it's just one feature of what we try to do, but it was resonating with a lot of people, so we put it a little bit more front and center. And this is also why the title of this presentation mentioned containers, but it really is just a smaller part of the whole offering in some sense. So if you now look at the way we do it, or our stack, is we still have the expressive and the free RTOS on the bottom, but now we add a virtual machine just above. And that virtual machine, for one, abstracts away the expressive, the ESP32, but it also means that we can then make sure that the virtual machine separates the individual applications, gives them resources, make sure the resources are correctly handled. Interestingly, the system application, the one that, for instance, scheduling the other applications, is also on top of the virtual machine. It just has more privileges, and then you can have multiple different apps that run on that virtual machine. And this setup has many advantages. I mean, aside the ones, obviously it has the ones that we wanted to have in the beginning, but by having a virtual machine, you also end up being independent of the underlying hardware, at least to a certain point. So that means we can run these applications also on our desktop or on Linux ARM. I mean, that's at least the three that we currently support are desktop, Linux ARM, and the Espressive. And it's not hard to basically just, it takes a week or two or maybe 3 to port it to another system, Sapphire or some other big interesting chip. But it means that somebody that has already everything, has a product ready, and then wants to switch to a new chip, doesn't need to do everything again. They can just make the Toit virtual machine work on the new chip, and then the whole applications, all of them, should just continue working. As long as you also make the hardware stuff work. There's a little bit of mention here of battery awareness, but that's, we switched to open source where we lost a little bit of this at the moment, but not necessarily in terms of it's not possible anymore. It's just not as automatic as it was on this slide. So I should probably update this slide. A typical question that comes immediately is, what about Python? Did we write it in Python? If not, why not? And it turns out the first attempt was actually to create a faster Python VM, to make this just with Python. And we discovered that Python isn't really designed for microcontrollers. Even on the desktop, I would say it's not really easy to make it fast. There's a reason it's not known for that. It has some properties that make it hard to optimize. And MicroPython does a good job, but it's still working around the fundamental design decisions of Python. And so we decided to do a new language, which we called Toit.
Yeah, and I think that this is actually one of the questions I had written down. Like, I need to ask about this. Why a new language? Because this was one of the first things when I dug into your platform, is that, a new language. Oh my God.
I will have another slide on this, because it is obviously a good question, and I think there is no completely correct answer. You could argue either way, but I will try to answer that a little bit more in the next slide. Here's just the very first hello worlds of the Toit language. You can immediately see that there's some inspiration from indentation from Python. So it's an indentation-based language, and also we basically removed a lot of the usual noise, I would say. So there's no parenthesis, there's no semicolon. It's a relatively clean and nice language. So there were two things when we did the Toit language. One is that we wanted to obviously make it optimizable. It must be something that we can actually run on the small embedded devices. And the other one was that this time we wanted to do something modern. Dart, the language we did before, was designed to be something that is neutral. I would almost say boring. It was designed to run in the web browser, so we didn't want to alienate all kinds of people. It was something that was just productive, but not extreme in any way, or even experimental in any way. Whereas with the Toit language, we definitely felt like we have done the boring one, let's do an interesting one that we like. And we ended up by removing all the noises, as I said, and some other design decisions that, in my opinion, turned out quite well, but are not usually seen in other languages. Again, as you just said, the big but, wasn't there any other language that would have fit the bill, or was there no other way of doing this? Did we need to do a new language? I think you can clearly argue that no, we didn't need a new language. We could have just taken an existing one and adapted, maybe removed the parts that aren't working nicely and so on. Yeah. But if you do that, you end up with a language that is different anyway. You need to learn what are the differences. You cannot necessarily use all the packages that exist because they might not work with your system. And there are some design decisions that there are always some small decisions that annoy you. I mean, when you design for embedded devices, you just, every time you make a decision, you wonder, is this going to work nicely on the embedded system? That doesn't necessarily mean that the language is worse. It just means that you do some things, you don't allow some things, or you do allow some things. One easy example is a stack trace. If you can access a stack trace within your language, and for instance, even print it or get the string of it, you need to have the source locations in your program. And that means that you need to put a lot of wasted memory flash it onto the device, just so that you can say where was it that your program had a stack trace, had a problem. In Toit, for instance, we don't allow you to have access to the stack trace as a string level, and you get a stack trace, obviously, but then you need to take it to your computer and then convert it to something readable there. Now, if you run on a desktop machine, that's happening behind the scene. There's a small wrapper program that does this automatically for you, but the language itself does not have access to it. And these small decision points very frequently don't change the way the language feels, or the way it's not necessarily now feel like it's a low-level language or it's a limited language, but it makes the program, the language optimizable. Another example is Python and JavaScript, for instance, allow you to add a field to an object. The moment you do this, you basically cannot use the efficient dispatch methods to access methods on objects and similar things. There are some decisions you need to take that don't work nicely with embedded systems. And most of the existing big languages, Python, JavaScript, and so on, have issues in that sense. You could potentially disallow it. You could say JavaScript, you're not allowed to add a field to an object. But if you do that, you really lose a lot of packages because you just do that. And then there are some languages we just felt are not high level enough. I mean, high level is now a term that is very vague, but to me, writing in Go, which is something I did for a while, doesn't feel high level. It's better. I mean, it's basically on the C level. Yes, it has memory, garbage collection, and it has a few things that C doesn't have. But from the point of view of what I need to think about, it's very close to C and feels a little bit more to C to me than JavaScript or Python. And similar thing for Rust and C and C++. So yeah, in the end, we decided to make our own language. We obviously were biased. We had done one before. We liked it. So that's obviously helping. Once we had the language, or in parallel, obviously, we also created the Toit virtual machine. And that's basically the way Toit works is you take the language, then there's a compiler that compiles the whole thing down to bytecodes. And then you run these bytecodes on the virtual machine. And the virtual machine, basically from our measurements, is 10 to 20 times faster than MicroPython. That's clearly dependent on the benchmarks you run it on. But given that we haven't even really optimized the compiler yet, we don't do inlining and similar things, I'm pretty sure it's in the ballpark. So 10 to 10 times faster than MicroPython is not absurd. Also, we have a very nice compacting sliding garbage collector. So if you use just the normal objects that you use in the language, it will from time to time move everything completely to, I call it left of the memory, and make sure that you don't have any fragmentation issues where memory just over time becomes less accessible. So from that point of view, it's really nice. A word on garbage collection channel. Very often we get these question: isn't the garbage collector the worst thing that could happen on a microcontroller? I mean, you need to have sub-millisecond thing responses and so on. And there are two important things, two good answers to that, or two good points to that. One is that the Espressif, the ESP32, basically does almost everything for you anyway. So you don't really do bit banging yourself. You ask the ESP32 to send on the UART. You ask the ESP32 to use the infrared module to send some bit pattern on a pin. You ask the ESP32 to do the I2C communication. So all in all, you very rarely actually need to be extremely precise in terms of timing. And then the other thing is that you only have not even 500K of memory. So running through the 500K of memory for a GC doesn't take that long. On our machines, where I think I have more than 64 gigabytes of RAM, yes, the garbage collector, if it needs to do a whole lot of garbage collection, can run through several megabytes easily. But on the small devices, you don't have that much memory, so the garbage collector doesn't take that long usually. Given that we have a language, it also needs some tooling. So we do have a language server, and that pretty much means you can use any IDE that supports the LSP protocol or the LS protocol. And I would still recommend Visual Studio Code, but I frequently use VI as well. The main thing that you might not have if you use a different IDE is the syntax coloring. That's something that does not come or did not come when I wrote the server with the language server protocol. So yeah, if you use Toit, prefer Visual Studio Code.
Yeah.
We also have a package manager. It's just a necessity nowadays and a good thing. And fortunately, I mean, we base ourselves on Git, so fundamentally we should have no problems of scaling and similar things. Authentication also is basically handled this way. There's a lot of we try to keep it, to not be involved in the server parts, about not too much at least.
Yeah, I got the question here. So, yes. Like, is Toit faster because of devirtualization and keeping things in RAM?
No. So the biggest reason for why Toit is faster than MicroPython is that we use a dispatch method, a way of dispatching methods that depends on the objects being stable. And when I see objects being stable, I mean that you create a class and then you know which methods are on that object. Whereas in Python, you can add fields and I guess methods, I'm not 100% sure, but you can change the layout of an object over time. And that means that you cannot implement these very efficient dispatch methods. Then there are other things that the virtual machine is clearly we spent a little bit of time of making that fast. And so fundamentally it's because of dispatching and because of a good VM, good virtual machine. So getting back to the slide, yes. So we also have fleet management, which allows you to update multiple ESPs, 32s at the same time, or install applications and remove them, update one, but keep the other one running. That's on console.io. You can definitely play with it if you want to see how this looks, but I would recommend to stick with the open source version, mainly because we're in the process of rewriting it and doing it over MQTT. As I've heard, you will have an MQTT course soon. And that is just the better way of doing it. So instead of going through our own servers, going through an MQTT server you control is just better. And so we will probably eventually discontinue the console.io offering.
Okay.
Then we have another tool, Jaguar, and that is the tool we use to develop with the ESP32s. And Jaguar is, we basically describe it as live reloading for your ESP32. And what we mean with that is that you can run an application within a second or two and update that application again within a second or two. The way this is implemented is that Jaguar consists of two fundamentally programs, one that runs on the ESP and one that runs on your desktop. The one that runs on the ESP serves a small HTTP server, and then the command line sends on UDP broadcast requests to basically say, I have this application for you, install it and run it. And that means that as soon as you are in the same network, you can just run the applications. It just works, and you can update applications. It's very nice. And I think that's now, yes, that's the time for actually showing
demo.
So I'm going to make a small demo and start coding it. Let's hope no, that's not what I want. Did I not? So let's hold it. Let's create a new file. This is better. Let's say main world. Let's just make a hello world and save it so that we have a file. Is that how it's written? I think so. Save. Good.
Yeah.
Now I will show a small setup here. So this is just an ESP32 with 3 I2C devices and an LED. Sorry. I'm not going to make all of these 3 I2C devices work. It's not necessary. But I will play a little bit with the LED, and I play a little bit with the BME 280, which is a temperature sensor.
Yeah.
And so I've connected this whole thing now to my computer with the white cable. I'll move this a little bit to the side again. And let's make this big. And now I have the terminal open here. And I will just Jaguar flash this device. So it's going to use TTY USB 0. It wants to know my network. Let's try not to mistype it now. And it's flashing it. So this is now the step where we put the FreeRTOS plus the virtual machine onto the device. And also during that flashing, we are going to install the Jaguar ESP version. So in theory, now we have on the device running a small Jaguar server that is listening to what we want to say.
Yeah.
And we're going to verify that by looking at what the serial output says and connect. And unless I mistype the password, which I did. So let's just again.
But this is supposed to happen when you do a demo. So
let's hope this was the one and no other one. But yes, and let's flash again. And hopefully I didn't mistype my password this time. And it should just go online and listen on UDP over HTTP just to see whether somebody connecting is connected. Yes, so it's connected. We automatically give new names to everything we flash. So in this case, it's called Genuine Disease, which is a very fitting name. And let's just, yes. So next step is I will create a new terminal here, is to run this. So basically I've already written this small hello world one. So I can just check run it. And now it asks me which device it wants to use. So I have another one in my doorbell that is also online, but we will use this one instead. And so it just ran the hello world. Now we don't see any output here. That's because the print by default, and we haven't changed it yet, goes to the serial output. So it's here in the serial output.
Yeah, I see. Yeah.
I'm sorry. Now it's clearly a little bit annoying to switch forwards and backwards all the time. So what I'm going to do from now on is I'm going to use Jaguar. And what Jaguar does is that every time, so it starts by immediately running the program. And then every time you save it, and let's just save it and edit something and save it, it sees that the file has been modified and immediately sends the new version to the device. So from now on, I can just keep the monitor running here and just every time I save, it will just nicely immediately update. And you can see the time to run a new program takes around a second, maybe 2. It's extremely fast. One thing I want to mention before I forget, I'm using GitHub's Copilot. So all the gray completions that you see are not from the language server, they are from Copilot. And Copilot has been trained on Python and other languages. So it's not yet completely tuned for Toit. So sometimes the completions don't really make sense. It's using parentheses where it shouldn't. But all in all, it's actually pretty good at also just working for Toit. In this case, for instance, it realized that, yes, in Toit, you don't use parentheses. You can just do it this way. I'm not going to complete it this way, but if you see bad completions, that's not the language server, that's Copilot. The language server completions are these. Yes. Next step is usually the LED. And that's what I'm going to do. So LED is GPIO, so we're going to import GPIO. And then the LED is connected to this orange cable, which is pin 32. So let's just make a constant 32 and create an LED pin. That's GPIO, that's pin 32, and we want this to be an output. We use dash and then something as named arguments. That's a little bit reminiscent to the console, and that's where we kind of got it from. And if you don't write equals, it automatically means equals true. So that's just a shortcut for equals true. So we can now set it to 1, then sleep, maybe let's say a second, and set it to 0. And the moment I save it, I will just make this big again and hope that it has the focus. The moment I save it, that's what it goes on and off. So that was just the hello world of embedded devices.
Yeah.
And now we can continue with a little bit more interesting things. I will see if I can go full screen.
Yeah. And the nice thing here is that, well, what we have done here, that there is no setup of the Wi-Fi, for instance, in the code. That is already up and running.
Sorry?
Yeah, the Wi-Fi, the connection and everything, that's already up and running. So
so when we flashed the device, we had to give it the password and the Wi-Fi credentials.
Yeah.
And that means the system currently remembers the password, and Jaguar is just taking care of that. We will actually use network a little bit later, so I can then show how this works there. But I think the next thing we want to do is use one of the sensors that is on this small demo board that I have here. And the sensor I'm looking for is the BM. So let's just erase the GPIO pin. We might get back to it. Oh, actually, what I should have done here is obviously use the constant. But next time. So we have a sensor which is called BME 280, and that's a relatively common sensor. So we actually have a package for this. So I'm going to open a new terminal and then ask Jaguar to search for the BME 280 and give a verbose output. And this is basically, you can see it's written, it's on GitHub Toitware, so it's written BAS, but it's a typical environmental sensor. It has temperature, pressure, humidity. It's classic. So the way we use it is just telling Jaguar to install the package. So we're going to install the BME 280, and now it's installed. I'm going back to the monitor here to see when we change the program and it works. So once you have installed the package, you can just import it and use it. Since the BME 280 is an I2C device, we also need the I2C library, which comes with Toit. And now I need to look again at the cabling. It's not sharp. Yeah, it's not going to work. Anyway, there is a blue and a yellow cable. Now it's working, yes. Blue and yellow cable, and the blue is 25, the yellow is 26. And I've written down that blue is SDA and yellow is SCL, so data and clock. So we can just say SDA, that's 25, and SCL, that's 26. But that's what we need for.
But the Copilot works quite well.
Yeah, it is, as I said, it's very impressive. But here, for instance, it says it's trying to do something with parentheses, which will never happen in Toit. So I use it because it's really convenient, and I will use it several times now in this demo, but it sometimes gets stuff wrong too. But the bigger your file is, the more it realizes that this is the syntax you use, and it's pretty good. I'm definitely impressed.
Yeah.
So let's just create a nice great C bus. So that needs an SCL, which is a GPIO pin. So again, we're using named arguments. So it's almost doing the right thing here, Copilot. And so the bus takes 2 pins so that it can run. You can also give it a frequency, but normally the bus frequency, default frequency works. There's just some devices where you need to make it slower. And then here we can just say scan and print the devices. So this is just the first step. So we created an I2C bus, and all of these, I will show that again on the, I'm not sure if you have learned about I2C or not, but I2C is a bus. So you have 2 cables, the clock, in addition to power and ground. You have 2 cables that the data and the clock that go from one sensor to another, and then each sensor just advertises itself when you ask for who's on this bus. So in this case, we have 3 different devices, 3 different sensors, and they all showed themselves. So we have that's here at the output, the bottom. We have 3 of them.
And you got 3. Yeah.
Yes, I now know that the 119 is the ID of the one that I want, but we actually don't need to know that. Normally, when you talk about I2C IDs, you talk about them in hex. So I will just change it slightly to say, call this, this is a bad completion. Go over all the devices and then print them, but this time print them using the hex notation, and the it is the implicit parameter. So what we do here is we call the do method on the set of devices and give it a lambda block, which you can think of like a function. So the moment you write colon and then code, it's basically almost as if it was a function. And the it is the argument that it got. So if you do this and we run it again, we now have the hexadecimal output. And normally you would use this. So now, as I said, I know that the 77, I think, is the BME 280, but I don't even need to know that because, I need to slightly know it because we are now going to get this device by asking the bus to give us a device. And we are going to use the constant that is in the BME 280 library. And it turns out that the I2C address, I'm going to it now, is 76, that's the default one, and the 77 is the alternative. So we need to use the alternative one here. With that, we can now create the sensor, which is just a BME 280.power of the device. And once we have the sensor, we can read, for instance, the temperature and print it. And hopefully, yes, it's 27 degrees. It's a little bit warm here, but I like it.
It is.
No, this is fine. This is perfect.
Yeah.
Now, let's just use the nice capabilities of Copilot and also get the remaining 2. And then we might as well print everything nicely in a line. And hopefully, nope, humidity. Yes, it completes automatically for us. Copilot is fun. So now if we print this again, we have everything nicely in one line. I will remove the print of the devices. And next step, almost certainly, is you're going to go to do this in a loop. I will just do it 10 times. And then sleep a little bit after every read. So now we run 10 times, get the temperature. It's still the same every time, so that's good. And this is running. So this is just to show how easy it is generally to access the I2C devices. SPI devices are very much similar, and with that you cover 90% of all sensors. And I think with that, the next step is basically use them on the internet. After all, it's IoT, it's internet. Yeah. And I will basically show a little bit of an easy way of making this work with the internet. And for that, I'm going to go out of the editor and do a little bit of advertisement for Adafruit. So Adafruit has this offering, and I think I will try to make this bigger.
Yeah, make it. Yeah, that's fine. I think so. Yeah.
Okay. So Adafruit has this offering where you can get a free MQTT server and a database on their webpage. You just go to io.adafruit.com, sign up for free, and then basically you start where I am now. And they have an MQTT. They have severe limitations, like you can only send data once every 2 seconds, and you can only have, I think, 5 or 10 streams. I mean, let's see, you can have 30 data points per minute, 5 dashboards only, 10 feeds. So 10 feeds means you can only have 10 different topics for MQTT. You will learn about topics soon.
Yeah.
But there are severe limitations, but it's good enough for simple projects, for sure.
Yeah. And also, I think that there's a lot of students that usually end up using Adafruit, even though we haven't advertised it. People find that as a good option to start playing with. So
it's I mean, there are others, but it's definitely one of the most known, and it works for 1 simple or 2 simple projects. The moment you have more than 10 feeds, and that happens fast, you need something else. But if you just do it for yourself, it's perfect. So I'm going to add a new feed, which, as I said, is a topic basically in MQTT terms. From 280, created. And this is now a place where I can send information to.
Yeah, perhaps you can make it a little bit bigger, I think.
Of course.
That's better, thanks.
Yes. So this, I might as well go full screen. So this is so this is something where we can send data to. At the moment, it has nothing, and you can normally see it down there, the individual data points. So next step is sending data to them. And as almost every, no, that's the wrong one. As almost every, that is, IoT project, they use MQTT. In Toit, MQTT is a package again. So we are just going to install it. I mean, we can search and show it first, but it's an MQTT client, it's a package. So we are going to install it. Go back to the output here. And we're going to make an MQTT client. So for that, we're going to use the network this time. And we're going to import the MQTT that we just installed. And let's put it on the top. The MQTT needs the network. So the first thing we need to do is open the network. So this means that we are going to ask the Toit system to give us an interface to talk network fundamentally.
Yeah.
And in this case, it's the Wi-Fi, because that's what I configured. But you can easily make the network open, the default one to be Ethernet, or you can create your own network that talks through some different means, like cellular or some other way. So there's an interface that abstracts away how you connect to the internet. And by default, it's just the Wi-Fi. Similarly, we have another abstraction that is the way of how the MQTT wants to talk to the internet. It has basically a transport interface, which is just an abstraction of I want to be able to read, write, and so on. And by abstracting it away, you have a way of creating a test one, or even, for instance, sending it through some weird way, let's say Bluetooth to another ESP or something. It's just another abstraction layer. I know by heart that the host for Adafruit is io.adafruit.com, I hope. Yes. So this is just creating a way to talk to it. And now we can create a client with a named argument. We're almost there. The main thing that is now missing is we actually need to start. We need to connect to the client, which is basically starting it. But we need to give it a username and password, and these are going to be inside options. Just scroll up a little bit. Oh, there we go. And the options is MQTT session options. We give it a client ID, which we just call demo. a username, which we will have fruit.io username, which we will have to find on the web page, and then a password, key, which we'll also get from the website. So if we go back to the here to the Adafruit website, there's a my key on the top right, which gives us all the information we need. And I'm just going to generate a key here and copy paste the information that they give us here. Yes, you could now send data to my Adafruit account. I will reset it later. And I will copy that in here. It's not yet Toit syntax. We need to make this a constant. And now basically we have set up the options and we can start the whole client here. And then when we want to send the data, we just say client.publish. Again, publish is a typical way of using the MQTT. And the way Adafruit works, it has its own semantics of how to access the feed. And here we just set temperature to byte array. So when you send the data to a MQTT, it needs to be a byte array. So I'm just converting the temperature first to a string by putting it into a string and then converting it to a byte array to send it. Also, we really don't need the quality of service. So we just set it to 0 here. Finally, before I run this program, I'm going to make this 2.5 seconds, because otherwise we're going to run into the rate limitation of Fruit. So I'm going to save this now. And then it's running again. And now if I look on the web page, here we can see that the data points are coming in. And we have the list of data points here as well. We could download them. As long as we don't submit more than one data point every 2 seconds, we can just, Adafruit is just happily storing the data for us and giving us access to it. Sorry. So this is now how we get the data to Adafruit. And the next step is actually making something nice with it. Again, this is more of a, no, this was the next thing is doing something nice. This is more of an Adafruit, again, show off, but you can create a dashboard. You can then show where you can add, I will switch from dark mode to white mode. I can create a new block, which is basically a line chart, for instance, that takes the temperature and just shows it. And so I have the block here. And if I now send again the data here, let's just start this whole thing again. Then we should eventually, maybe we need to enter it again. Yes, it's showing the temperature. So this is just a very nice, convenient way of showing and keeping track of data. And there's one last thing I wanted to show on the Adafruit is they also have a way of sending data from the dashboard to the device. So I'm going to create a new feed, which I call LED, and an on-off. So we have an on-off button now. And in our program here, I'm going to create the LED pin again. Let's remember this was just this line. Nope. No, this is just output. That was GitHub Copilot doing something weird.
Yeah.
And then I can say client.subscribe to, again, it's actually doing the right thing, but it's nicer if it's using this feeds LED. And then this one will call this lambda here, which we then say LED set payload to string equals on 1 or 0. So as soon as we press the button when we run this program again, it will subscribe to the topic on Adafruit. And when it receives a new message, it will take the payload, convert it to a string, verify if it's on, and if yes, set the LED to 1 or not. So now we will take again the video and go to the web page. And if I press on, it's on. And if I press off, it's off.
Yeah.
So this just shows that really, if you have the right tools available, you can. I mean, this is just an LED, obviously, but if you had a servo or anything or any relay or something, you could just immediately within. I think it took me 25 minutes. You can control basically what you want.
Yeah.
So, and I think that is what I wanted to show for my demo, at least.
Yeah, and let's say that I want to run yet another application, that I have a couple of it. We're talking about these containers. So if I have another sensor, I want to connect to something else or do something else. Should I start implementing that in the same program, or should I?
So at the moment, I would say there are different ways of doing this. At the moment, I would just start in the same program, but we do have ways of spawning different applications, which is actually what Jaguar does. Jaguar itself is not big. If you want to look at the source code of Jaguar, it's really not big. The main thing is we haven't really made it easy for Jaguar to just say, I have multiple applications installed. That will come soonish, but at the moment, it's probably easier to just try to run it in one application. We have a way of running tasks, which are cooperative threads, and there you can just run multiple independent things. But if you want to run actual real applications independently, currently you run only Jaguar and the kind application. If you want to run more than that, just chat to us and we will show you how to do it. It's not that it's not possible, it's just that we haven't exposed it at the moment. But Jaguar and the application themselves are already two different programs that run at the moment on the device.
Yeah.
So let's go back here. Yeah, so this was the demo. So what I didn't show here is, and partially time, partially because it's sometimes a little bit more complicated, is cellular. We do have a few customers that use cellular, so we needed to spend a little bit of time to making that work nicely. It's a rat hole, to be honest. It's cellular connections are not very stable, but we think we have something nice now. I didn't show deep sleep. Writing to flash a display, we have a nice library to use displays. So I think some of you have the health tech devices, I think, have displays. Yeah. So they might be nice to use there. Bluetooth, only BLE, but still very nice. And then if you have LED strips, use them, play with them. It's extremely fun. And if you don't have them, get them. It's one of the, yeah, it's very nice to do something that is visually appealing and so productive in terms of getting something done.
Yeah. So in terms of the platform, you mentioned that earlier that when you go to your web page as it looks now, then you focus much on the actual console and the platform, but that on the roadmap, that is something that you're like.
Yeah, the roadmap is mostly going towards the open source version and less towards server-based things. We don't want to run servers fundamentally.
Yeah.
We want to offer a product that makes fleet management easy. So we will give you the tooling, fundamentally the programs to do this, but it will not be on the web. It would just be individual applications. And but yeah, so fundamentally, I would say the Toit.io currently is still focused on containers and similar things. For students in general, I would almost always go with the open source one anyway. Yeah. And we are in the process of making that work, the app installation of individual applications and similar things, so that if you need something like that, just chat to us and we either give you tips or give you access or something similar. What you wouldn't get is this nice UI that you have on Toit.io.
But yeah, so I just show the picture. So this now I'm showing your website as it looks at the moment, and you have this console. Actually, this is me playing around. It's actually not anything running on that at the moment. But the thing is that this is well, the cloud-based version. Yes. I would say, yeah.
So fundamentally, I think toitlang.org is more in line with what we currently push people towards, and Jaguar itself on GitHub is the other one. Eventually, again, we will have something similar, maybe not as beautiful, but functionally, and it's going to go over MQTT, which is just the standard. We have something running on AWS and Amazon MQTT, and updating over MQTT, the whole firmware, is something we recently managed to make work. So we are switching towards something more standard and not our own protocol and our own service. It's not only that people don't like that. Generally, it's also that, honestly, we are not server developers. Yeah. And while we managed to make this work nicely, it's not what we like to do. We are more the tooling, virtual machine developers, and we will try to make that work instead. Yes.
Yes. So I'll see if I got a question here. How's the Toit library ecosystem? A question.
Yeah. Okay. Let me just get out of that screen again. The ecosystem depends. We have improved dramatically in recent months, I would say. In particular, the most important peripherals of the ESP32 work. We have drivers for many of the important sensors. I mean, I used the PME 280, and yes, obviously I used it because we have a driver, but there are quite a few SparkFun and similar drivers similar sensors that work. If they don't work, often it's register-based. I2C devices are often just, I send to a register and I get a value back. So they're very often easy to implement. And if not, we try to make this better as well. So I would say it's medium. It's to a point where I would look on package Toit.io first to see if the driver is there. If it's not there, I would either see if it's easy to implement or ask if somebody can help. But I would say that most of the time it actually works. So I have, for instance, this MakePython ESP32 dev kit, and that is fully functional. So everything in there works, including the display, including the distance sensor, and so a lot of sensors and drivers work. And if not, again, just ask us if we can help or if we can even do it. But I would say it's medium to good now. Still missing stuff, obviously. We're not as big as MicroPython.
Yeah, so this is, there are no more questions at this very moment. So
and I might show the last slide page just to give pointers. I'm not so. Yes, so as I said, as a conclusion, it's a better way to develop the ESP32s. But more importantly, I wanted to say, yes, we are completely open source. And if you want to chat with us, here's the Discord link. And you can find that link also on toitlang.org. At the bottom of the page, there's this very small Discord icon that gives you access to it, that shows you where the Discord is. So yeah, if you have questions or something, just ask us. Yes.
Great. Yeah, and I'll make sure that you get an invite also to the Discord server, so you might be able to at least pick some questions from the students. And there is, I think that you have in your documentation, there are a lot of tutorials, like what you showed now in the live demo. You'll be able to find, I guess, quite easily in the documentation.
Yeah, so most of the time the packages have an example folders. So if you go to the repositories, there's almost always an examples directory, and there you can find some examples. And the Make Python, again, that one here, I wrote a big, I think now it's 70-page Google Docs document that really hands-on, one by one, step by step, goes through it and shows you how to do it. It doesn't, for instance, have the MQTT or the Adafruit thingy, but if you want that, I mean, either you have the video now, or you can just chat to me, and it shouldn't be hard. The whole point is that.
Are we able to share that Google Drive document
yes,
with the students?
So.
Yeah,
okay. Just go ahead.
I'll do that. Yeah.
Good.
In that case, I thank you very much, Florian, for this very, very nice session. Some live coding before lunch. It's always nice.
and only one big Wi-Fi password being wrong thing. So it worked quite nicely. Yes.
Yeah, I'm very much impressed. So I see that you have some experience in this area. So
great.
Okay.
Good. Thank you very much for having me.
Thank you.